So, hello, ladies and gentlemen. Welcome to the lecture in Computational Fluid Dynamics, Chapter 6. Today we will speak about turbulent flow and eddies. And at first, we want to look at a normal laminar pipe. And if you look at the flow inside a laminar flat pipe with flat walls, you can see the velocity profile and the velocity profile after some a special distance will be here parabolic, more or less. And you can describe the turbulence inside this pipe by the so-called Reynolds number. That is more or less easy. Reynolds number describes you if the fluid flow is laminar or if the fluid flow is turbulent, and you can calculate it by velocity of the fluid inside the pipe times diameter divided by the viscosity of the fluid. And this is, this will give you a hint if the fluid flow is turbulent. If the Reynolds number is below 2320, it is laminar, and if it's higher than 2320, the fluid flow is more or less turbulent. But we have to look a bit more into detail of turbulence now. First, let's have a look at this laminar region. This is a region lower than 2320, and we describe the fluid flow, the laminarity here, with the so-called lambda value, the friction coefficient, and this was first formulated by Mr. George Gabriel Stokes, and he described this friction coefficient in the laminar region by 64 divided by Reynolds. This is easy. It's an easy description, so you can calculate your lambda value just by 64 divided by Reynolds if you are in the laminar region, if you're here below 2320. So laminar flow velocity, it's summarized. In case of laminar flows, there is no cross mixing in the y direction. Heat transfer occurs only by heat conduction along the temperature gradient and the thermal boundary layer. And the boundary layer thickness depends on the run length of the pipe. Okay, but now it gets a bit more difficult. What happens if we are higher than 2320? Here you see the full diagram. We have the laminar region with our curve here, 64 divided by Reynolds. And the description is rather easy. But now if it's getting turbulent, the behavior, the friction is totally different. It rises, and it depends really much on the roughness of the walls. If you have laminar flow, the flow does not depend really much on the roughness of the walls. But if you have turbulent flow, roughness is getting more and more important. This can also be roughness of walls of pipes can be described by the so-called centigrade roughness. And to visualize this, you can you would call this kind of diagram Nicorazzi diagram, or from time to time it's also called Moody diagram. Here we have just another version of this diagram. It's a so-called Moody diagram. Again, we have our friction coefficient lambda here, we have our linear region in the laminar flow field. It's just 64 divided by Reynolds. It's just a line, but we also have the turbulent region here. And in this turbulent region, we have many different kind of friction coefficients, and they depend pretty much on the roughness of the walls. So here is our Reynolds number. Yeah. Reynolds number, you already know this, is one of the most important numbers in fluid flow. Reynolds number can be calculated by density times velocity times the characteristic length, for example, diameter of a ball or diameter of a pipe, divided by the viscosity. And here you see fluid flow in a laminar region. That's more or less easy. Its Reynolds should be smaller than 2320. And in the turbulent region, it's getting here, it gets this swirl region. Okay. Now you have the question, why do we need this for CFD? And this description is one of the most important results from CFD. You can see it in the CFD results. Yeah. Here you have, and you can also see it in CFX. Yeah. You can see the convergence here of a turbulence model in CFX. You know this solver manager, yeah, and normally you look here in the first folder, momentum and mass. There you can see the residuals of the momentum equations U, Y, W, and the mass balance here, P mass. But there is a second folder here, and there you can see the convergence of the turbulence model. Yeah, and for the turbulence model, you need two additional differential equations. You need a differential equation for K, and you need a differential equation for dissipation. Yeah. So, yeah, and that's something I have to explain you. I have to explain you what does K mean, what does epsilon mean. Yeah, how can we solve turbulence by a differential equation? If you look at this picture, you see turbulent flows, yeah, and of course, you can see on this picture that it will be just really difficult to describe this with differential equation. On the left side, we have a sketch, and this sketch was made by Leonardo da Vinci. He was a really famous scientist, and he made a lot of research in turbulent flow, and he made a lot of research in many different kinds of sciences. Yeah, and he also was really interested in building ships and building bridges. And if you closely look at the water flow around ships or the water flow around a ship, yeah, you see it behaves turbulent. And he tried to paint it, yeah. And he didn't do this for fun, or not only for fun. He did this also to examine the fluid flow, yeah, to visualize it. Here you have, and you can imagine this is really difficult. If you just look at the water and you try to paint it, that's not easy. Yeah. Here on the right side, you see another picture, and I copied you the picture to the slides because I think this is a really nice picture, and it shows you also turbulent flow. You can imagine this are swirls, this is turbulence, and it looks really pretty. And I think you can never imagine what it is. it is a satellite picture of the ocean. Yeah, and these are small, like small animals, and they give a color to the water. And you see, and these are really big swirls. Yeah, they are many kilometers long, and they look pretty much like the small swirls. Yeah, that's important for turbulence. The turbulence and the swirls, they always look similar. Yeah. Yeah. So turbulence is found in many areas of nature and technology in various forms. It is known that even in bright blue skies, aircrafts can be stimulated by a strong shaking. So even if you do not see the turbulence, it can affect you. It can affect you. Yeah, it can influence your fluid flow. Yeah, or for example, for the premixing process in flames, they can pretty much influence you. Here you have two pictures of turbulence behind an airplane. Here you see an airplane. It flies through the clouds, yeah, and you have here this words, yeah. You have clouds, yeah, and these clouds, these are influenced by swirls, yeah. You can see here. And normally you cannot see these swirls. Yeah, this was a really special case where the airplane flies directly over the clouds, and the swirl mixes the clouds together with the fresh air, and this forms these swirls. Yeah? Or you can see it here. You can see also swirls. Yeah? And the swirls influence the fluid flow. Yeah? And this is also a special picture. You can normally it is really difficult to make such a picture, such a good visualization of the swirls. And where does the swirl come from? The swirl comes from the tip of the airplane here. There is a swirl that rolls over the wing and forms a swirl, and the swirl is getting bigger and bigger and bigger. And even if you do not see this swirl, it is there. For example, if you have a really big airplane, for example, an Airbus 380 or so, and it produces a big swirl, and this can influence other airplanes. Yeah, other airplanes can be pushed down to the ground by this swirl behavior. Here's another picture of this kind of swirl behavior. Yeah, this is a small video from a yeah, small river. And here you have a stone, and after the stone there is this swirl behavior. Or you see it here, it's a simulation. You see this kind of Karman's vertex street. It's developing after this circle. Yeah? Or you see it here. Yeah? You have this ball, you have this stick, and after the stick you see this swirl behavior. And here we have another nice picture. And this is again a satellite photo. Yeah? And it's made of the Juan Fernandez Island in the ocean. Here you see the island. And also behind this island, you see the same Karman's vertex street, the same kind of swirls. And they are really big. Yeah, you see these swirls are yeah, some 100 meters big, but it looks pretty much similar to the small vertex street. So here again, you see this kind of vertices look pretty much similar. Yeah. Okay. Let's have a look how the vertices are formed. Yeah. You have here always after a body or after a cylinder, you have this kind of wake region. Yeah. You have this region of turbulence after the cylinder. And you have also a rectangular, or you can have a round body, or you can have a rectangular body. Yeah. And after this rectangular body, you see this kind of turbulence. Yeah, you see this kind of swirls. Yeah. So, or for example, you have a car. Yeah, this is a picture of a BMW. You have your velocities. They're more or less laminar here, laminar over the car. You have your pressure field, you have your laminar fluid flow, but after the car, you get a wake region. And in this wake region, you get your swirls. Or here is another type of wake region. And these pictures are not made by PowerPoint or so. They're really realistic photos. Yeah. This were really made by a photographer. Here you see fluid flow around the wing, and you see one stream of condensation. The air, the pressure is really low in this region, and so the water in the air condenses, and you see this condensation um, in this above this wing, and it's a good visualization. Yeah, it was not made by PowerPoint, by Photoshop. It was a real picture. Or even this picture, it shows you a swirl, and because the pressure is so low in this region, condensation occurs, and condensation happens to this stream. And that's also, it looks a bit funny, but the swirl here hits the ground. And that is what happens also to hurricanes or yeah. Hurricanes always try to touch the ground because it is less energy consuming for the fluid flow. Yeah, if you have a swirl or a small hurricane, it always tries to touch the ground and gets into contact with a wall. This is also an effect that happens in many technical applications. For example, if you have a valve, or if you have yeah, or fluid flow in a pipe, it can also happen like this. Yeah. Here we see really big swirl again. Yeah, it's a hurricane. You know this kind of swirls, and also these swirls behave similar to other swirls. Yeah, you have your in the middle. You have it's a so-called eye, and you see here the wind velocity is not very high, but the pressure is really low, and this can also cause yeah, it can suck up the water of the sea, and that is a really big problem that can really much influence yeah, if the hurricane goes over an island or over a land or over buildings, it can push the water from this water dome also over the land, and then it can destroy pretty much of the housings and pretty much of this land side. Yeah. Okay. Here are other pictures of vertex streets, and look a bit funny, of course, but they are realistic. Yeah, it's not made by Photoshop or so. They really look like this. If you have a great plane, a big flat land, you can see this kind of swirls. And I can tell you, I live near city of Landstuhl, and there we can also have sometimes this kind of swirl regions. Yeah, you can sometimes see it in the clouds, that you have regular cloud formation. And maybe one thing I want to mention here, um, the swirl have always two different kind of swirl regions, but you only see one. Yeah, you see the lower swirl region because here is water steam, yeah, clouds, but there will be also the same swirl region above, but we cannot see it, yeah, because it's too high or there are no clouds. And here also you see sometimes this swirls are really big. Now they can even go over the houses here and cause swirls. Okay, and you can imagine for this houses, it's really important to calculate it, to make a simulation of the swirls, because you do not want this to happen. Yeah? Okay, here we see this creation of the swirls. Yeah? At first, there is one velocity. Fluid is, yeah, is be transported laminar by the momentum, and this causes at the upper side kind of swirling, and at the lower side it influences here your swirl. Yeah, you get rotation region. Also, if we go back to the hurricanes, this kind of swirls, they always, when they are builded, they're at first in a vertical region, and then after some time they get they're first always in a horizontal rotation, and then after some time they get vertical. Then they hit the ground. The eye hits the ground. Okay. Or you can have this single swirl, or you can have two different swirls. Then it looks like this. Okay. There's also there are also some experiments. I've shown you some experiments before, experiments I made in our lab for fluid flow behavior. But you can also have here this famous experiment from Hagen and Reynolds. And Reynolds made this experiments because he examined a lot in tubes. He examined this. He wanted to build pipe systems and tubes, and he invented this so-called Reynolds tube, where you can really visualize the turbulence. And that's something I've showed you in the movie before. You have a tank with colored water, and you have or ink or so, and you have a normal water tank, and then you have a laminar flow in this pipe. And after some time, the turbulent gets a bit swirly, and you get this turbulent region. Okay, and you can watch this movie by clicking on the link or by copying this QR code with your smartphone. Okay, here is the next swirl behind the tube. Yeah, you have here this tube again. Now we have made some visualization with smoke, and in the wake region you see turbulent swirls. You can see turbulent behavior. Here again is another picture, And this picture was also made by Schlieren Photography. I've shown you some Schlieren pictures before, and this is again a Schlieren picture of a candle. Now you see here the candle and the fire of the flame, and with this Schlieren photography you can also visualize the fluid flow. And the air gets hot here, and at first you have a big laminar region, yeah, where the fluid rises, and after some time the fluid gets swirly and turbulent. In the turbulent region we have Reynolds numbers bigger than 2320, and they can be much bigger. This is not really true, this 10,000, the Reynolds number can be pretty much bigger. And in the laminar region, we are lower than 2320. Now, how can we describe this flow behavior? Yeah, how can we describe it mathematically, this swirling region? To describe it, you can formulate the so-called Reynolds averaged Navier-Stokes equations, so-called Reynolds numbers. And you already know the Navier-Stokes equations. Yeah, the Navier-Stokes equations are more or less momentum equations where you describe the momentum balance of the fluid. And the so-called Reynolds average Navier-Stokes equations include also a description of turbulence. And if you look back at this picture, you can imagine this is pretty difficult. If you make a mesh here, you want to describe it, it's really complicated. And so it is also in this formulation. You need a so-called Reynolds stress tensor, tau, and you have to calculate all the fluctuations and derivations in a matrix for every cell. Yeah, this is here included in this turbulence description. Yeah, here again is a visualization of this wake region. Yeah, it's for different Reynolds numbers. And if you look, if we are Reynolds 0, yeah, we have a laminar flow, no problem. If we are in Reynolds smaller than 50, yeah, we get this first wake region, but it's already laminar. Yeah, you can describe it laminar. And if we rise up the Reynolds number, the fluid flow gets more and more turbulent after in the wake region. Another example of wake regions is also here shown in this in pipes. If we have a pipe here and the pipe gets wider, then we will have also wake regions here in these edges. Or we can have wake regions here in these regions. Yeah? So and if you look clearly at this pipe, you see it looks pretty much the same. Yeah, here is a small area and here's a big area. And this is the same geometry, but it's just turned around. So it depends in which direction the fluid flows. Yeah, the turbulence, it depends pretty much on the direction of the fluid flow through a pipe. And this can be for technical applications be really serious. Okay, and in the next section, I will show you an example from Bosch where we had this problem. Okay, Mr. Martin, can you stop the movie?